Okay, so let's get started here then. Thank you all for joining us on Zoom. Um, I know this is for most of you this is quite a bit of a change because you might be used to Google Meet at most. So I appreciate that you are trying this out. Okay, I will again tentatively encourage you to turn on your video camera. And if the connection is really bad, I have a couple of suggestions. One is to turn off your own video camera, but also the other idea might be to um, change the layout so you're not seeing so many video streams coming in. You're only maybe seeing the shared screen. All right. So please play with those settings if your video quality becomes really bad. All right. Um, all right, but I'm hoping otherwise that Zoom will provide us a little bit better connection quality for a class of this size. Um, I've tried to use Google Meet for a smaller class with less than 20 students, and Google Meet was just fine. People had no problems whatsoever with it. So it seems like Google Meet is having a problem with more than 50 people. Is there a question? I have I have started the stream, in fact. Okay, it is streaming right now, so I'll have to see later if there's an issue with it, but YouTube is picking it up, okay? All right. At least I can see on my studio console that YouTube is recording it and it's seeing the right thing. Okay. All right. Okay. But Halim, do let me know in a minute or two later if you still don't see it. Okay. Um, all right. All right. And what else? There should be a chat window here for Zoom as well, but I'm not exactly sure where it is. I have to find it myself. Let me go to um, Zoom window, mm, show chat. Okay, all right. So there's a chat window as well. Unlike Google Meet, Zoom can pop up multiple windows for different things. So I apologize that we have to kind of it's a slightly different setup. All right. Okay. So let's get started here. I'm going to let me try one thing. I might even try to put the chat window on the side here in my own presentation to see if it works. Okay, since it's a public chat, you can see what's going on here and you can see the questions. And it might help those of you who are watching on YouTube because then you can see the questions that people are asking and as and when I'm answering them. All right. And what else? So, like last time, I apologize that I'm going to have to adjust the material a little bit because it does take a little bit of time to get used to Zoom or to these online platforms. So I'm going to try to reduce the material a little bit that I'm covering today. And what I cannot cover today, I'll try to cover next time. So I'm using these couple of weeks to get us used to the online platform largely. All right. Before I get started, are there any questions about the online platform? Um, Halim, have you been able to find the YouTube channel streaming already? Okay, could I ask one other person? Could I ask somebody else to go see if the YouTube channel is streaming or not? Because YouTube tells me it is streaming. Okay. Okay, Edgar says it's streaming. All right. So we are live. So maybe we're just looking at the wrong thing. Okay. Okay. So these are the kind of adjustments we're having to deal with. Thank you everyone who's checking it. I appreciate it. All right, great. All right. So welcome to week 14. I have to remind us a little bit of the schedule. We are now in week 14. The semester has 18 weeks. The 18th week is actually supposed to be exam week. So we will have an exam that week, okay? Oh, everyone says okay. No, I'm joking. There's no exam in this class, so you can relax, okay? But nobody was complaining, so that's excellent. All right. There is no exam in this class, so and the reason for that is because your homeworks are a lot of work already. So if you've done all the homeworks, I trust you know the material. There's no point for me to make you memorize everything for one more meeting or for one more homework, okay? So how many more lectures are we going to have? We're going to have week 14, that's this week. We will have a week 15, and we will have a week 16. Um, and after that, the 17th week, Monday, is actually a holiday. And uh, of course, I can still stream, but I think a lot of you may be out doing family things. So we're not going to have class on the 17th week. What I will try to do, however, is I will try to have one last session on either week 17 or week 18. I haven't quite decided yet. Maybe on week 18, the same time as class. However, that last session, that last lecture will not have any homework or anything associated with it, okay? It's just a free lecture to come and listen to some special topics on computation. So the last lecture of this class will be a homework free, exam free, just a fun lecture to come and talk about some topics that um, are relating to computation, but not part of this class. So that's going to be the kind of schedule. So we really have just 3 lectures left, including this one. All right, 14, 15, 16, and then one more, like I mentioned, non-homework related lecture. All right. Okay, good. So that's this. That's our schedule for this semester, and hopefully we can get everything wrapped up while we're still taking care of everything else that COVID is kind of throwing at us right now. All right. Okay, great. So let me get started with this week's topic. And I want to revisit a little bit of what we did last week. And I want to possibly move into some new things as well this week. All right. So last week we were looking at regressions, and in terms of regressions, the last topic that we looked at a lot of interesting things about multicollinearity and about nonlinearity and about transformations and analyzing residuals coming out of regressions and things like that. And the last thing we looked at was this topic of moderation, which in a regression is represented by an interaction term. All right, and all right, one second. I'm just going to mute all your microphones because sometimes I can hear somebody saying something or doing something. All right. All right. And so we were looking at this topic of moderations and interactions, and I just had like to have a one last look at that. And we will do one more thing with regressions today before we move on to other things. So let's go back and talk about moderation, or what in regression we simply call an interaction. The question that was asked for your homework assignment was about how acceleration affects the fuel efficiency of cars. The acceleration ability of cars affects their fuel efficiency for different weight categories. Okay, and I asked you to look at light cars and heavy cars, and essentially we looked at cars that were above the mean and below the mean in terms of their weight. I looked at how this relationship between uh, acceleration and miles per gallon potentially changes between those two weight categories. Okay, so let's take a look at the code and let's see how I tried to go about solving it. And there's a few potential issues and pitfalls here, so let's try to explore those. Okay, so here's my code. And the handout also has it, but let me just kind of run through it through RStudio first. So I'm going to first load up my car's data set, and I'm going to right away transform it using the log transformation. Okay, and all right. Now, in the homework, I asked you to split this data set into possibly lighter cars and heavier cars. And one way of doing that is to simply take the mean weight and split and say the lighter cars are below the mean, the heavier cars are above the mean. All right. But actually, and I don't think anyone asked me this specific question about the categorizing the cars in light and heavy. There was a similar question about mean centering elsewhere. But I do have a question here, which is when I define light cars and heavy cars, should I look at the mean of the original car weight, or should I look at the mean of the log weight? So let me take a and by the way, I think both are reasonable approaches. There's reasons to possibly do both. But let me just take a quick poll. Could you raise your hand virtually with that little raise hand button if you took if you looked at the mean of the original weight and split the data set into two based on the original weight? Because you use the raise hand if that's how you split the cars by mean weight. All right, so we got one person, only one person. We got a couple. All right. Oh, we got a few people. All right. So we've got several people who chose to split the cars based on their original weighting. All right. Okay. Thank you. I'm going to try to lower all your hands now. All right. And just to make sure the rest of you are paying attention, how many of you split the car categories based on the log weight, based on the mean of the log weight? Could you raise your hand? All right. So it looks like a lot more of you split it by the log weight. All right. Okay, reasonable. Thank you. Thank you. All right. So I'm going to lower all those hands. Okay. So there's actually two ways to do it, and both are defensible, I think, but they just have slightly different assumptions. I do like the idea of splitting it by the original weight first because the original weight actually has more meaningful units for us, so we can think of it as basically looking at the kilogram weightage of the car and saying this is light or this is heavy. All right. I also think splitting it by the log is defensible because finally the analysis you're going to do is on the log weight. So you might also say that the weights themselves may have this kind of non-linear relationship with miles per gallon. So taking the log makes it more linear, and then somehow taking the mean is giving you something that's closer to the mean of the regression itself. So I think that's also quite defensible. But you just should be clear that there is obviously a difference between taking the mean of the original weights and the mean of the log weights. All right. Um, okay. And as long as you realize that both are possible and you can justify one way or the other. So I think that'll be an interesting difference. Okay. All right, great. So I took the mean of the log weights in my attempt at doing this homework assignment. Okay, and honestly, I think if you do it both ways, you'll see that the split is not all that different. They're in fact very similar in this data set. The log weight and the mean weights will give you a fairly similar split. All right. I want to describe a little bit about my code and like my style of writing this code. It might just be something that's interesting to some of you because we all have different ways of splitting it and creating the two categories. Okay, so the way I did it is this, and I hope that you can see my screen clearly. Is that I did this logical operation of just asking which log weights are smaller than the mean weight. So let me just run that for a second. Actually, before I run it, um, anybody want to guess what if I just run this part, car logs weight smaller than mean of car log weight? What am I going to get? Would anyone like to tell me? You can either type it into the chat window or you can raise your hand if you'd like to take a guess. All right, we're getting some answers in the chat window saying true or false. Hey, this is one thing I guess I do like about Zoom. Since the chat window is detachable, I can broadcast it to people watching it on YouTube as well. So that's great. All right. Yeah, so it should return true or false. So let's take a look at that. Yeah, it returns a whole bunch of true and falses. All right. And what you'll find is that I've taken all these true and falses and I've stored it into a variable called is light car. And this variable, the way I've named it and what it represents in programming, it's sometimes called a predicate. And predicate simply says whether a condition is true or false, or whether a condition is actually met. All right. So I've called it is light car, and this is a kind of predicate which is just telling me which cars true are light or false are not light. Okay. And you'll notice that my naming system is underscore, so that when I look back at this variable later, I can see that this I'm asking, is this something? It's a question. So by having this little prefix of is, I will know in future that it's going to be true or false. All right. If I just called it light car, if I just call this variable light car, it would be maybe a little bit hard to know whether this variable is holding like information about cars. Is it actually the data set of light cars? No, it's not. It's actually just true and falses about whether the cars are light or not. Okay. So since it's asking true or false questions, I'm kind of writing it as a question. Is it a light car? All right. So this is just a style of variable, and I just like to call them predicates. Okay. And is light car gives me those true or falses. Um, I can also define a is heavy car, and there's two ways to define is heavy car. One way might be just to take this logical expression and flip this comparison operator to making it greater. That would also tell me which one are the heavy cars. But an easier way, which uses the variable I just created, is just to say all the cars that are not light cars are heavy cars. All right. So if I say these are all light cars, then not light cars. So let me just look at the first is light car. Like the first few, they're all false, false, false. And actually, can I tell it to give me the first 10? Yes, that's all right. So just the first few is fine. And if I say not is light car, then those are all true. All right. So is heavy car is just the opposite of is light car. All right. Okay, so this is just a predicate, and this is a handy way of kind of creating a condition. And what's really cool is I can use this condition in other places in my code as and when I need it, and I'll show you a couple of examples. One example is when I'm actually then trying to extract the data and subset the data. I can simply say that um, light cars are just the cars where for with the rows in which is light car is true. All right. Here I'm looking for just the rows because that's what the comma does for me. So the first input into this into subsetting cars log gives me the rows. So this is one way I can just extract the light cars data sets. All right. So if I oops, excuse me, how do I get here? Head. All right, so this kind of gives me the first several light cars. And similarly, the heavy cars can be extracted like this. So I think using this simple predicates actually makes my code more readable. There might be other ways of making it more readable. And I'd be interested to look at your code later today to see how the rest of you did it. Okay. So I can also do a scatter plot, and let's take a look at my scatter plot, and then I'll explain my code. Oops, I haven't made enough space to draw the scatter plot, so let me make a little bit of space here. Um, Let me just clean this plotting area first. All right, and let me just plot these cars. And you'll notice here's the plot of the cars, and they're in two different colors. The light blue is for the light cars, the dark blue is for the heavy cars. All right. And how did I get them to appear at once? Simply in the plot command, I have a color specification. So I've told it what colors I want for each of the points. And essentially what you want to enter to colors is either a single color if you want to give them all the same color, or else for every row in your data set, you want to specify a different color. And the way I've done that is this. I'm using this if-else command and asking, is each car light or not? If it's light, then I want light blue, and if it's not, I want dark blue. All right. We've seen the if-else function, I think, sometime before in this class, but just to give you a sense of what it looks like. So is light car is again these true and falses. Okay, starts with a whole bunch of false, and then we have some trues. It ends with like at least 5 trues. All right. And when I do if else, it's asking, is this true? If it's true, then this is what to return. If it's not, then this is what's to be returned. And when I do that, I get a whole bunch of colors, dark blue, dark blue, dark blue, all, and everything is either light blue or dark blue. All right. And that's the vector that I'm passing in to the to colors. So I'm giving it a vector of colors so that each point can have a color depending on if it's light or if it's blue. All right. So this is, again, I think a good demonstration of where creating this simple predicate really comes in handy, because even my code for the visualization is much more readable. I'm basically saying if it's a light car, make it light blue, or else make it a dark blue. All right. Once again, I'm sure there's other ways of writing this code, but this is just my attempt to make it a little bit more readable with this little trick of creating these predicate variables. All right. Great. Um, all right. Let me move on. Uh, I've already split the cars into light and heavy categories. So now I'm just going to draw an AB line with the linear regression of miles per gallon log regressed over log acceleration. And let me just kind of draw that on screen. And that's for the light cars. And this is for the heavy cars. Okay. And you do notice here a slight difference in the slope of acceleration and miles per gallon, log acceleration, log miles per gallon, for the light cars and heavy cars. There's actually two differences between these slopes. One difference is that one is further higher up than the other one. That's not because of an interaction, though. That's just a difference in intercepts. What we're really interested in here is that the slopes are different. All right. So I just want to make this clear. Sometimes you may do a split regression like this. You're splitting the data set and doing two regressions. And you may notice that for one of the data sets, the regression line is higher than the other. That is not an interaction. That is simply telling you that the lighter cars, the relationship in acceleration and miles per gallon would be the same if the slope was the same. So what we're really interested in here is that the slopes are actually different, not that one is higher and that one is lower. Okay, so I just want to make that clear. All right. So that's my visualization, and that's my visualization right here of how to kind of see the interaction between um, the interaction of weight and acceleration on miles per gallon. All right. And then I can also examine the fuller regression. Notice that when I was doing the visualization, since I can only visualize in 2 dimensions, my regressions that I was using for the visualization is only in 2 dimensions. It's acceleration in miles per gallon. But the homework assignment is actually asking for more than that. The homework assignment is actually asking you to regress it over a couple of other factors as well, model year and origin. All right. So the visualization is not the complete story here. All right, so I then regress it for the light cars and for the heavy cars, and I noticed that almost all the other coefficients are fairly stable. Weight doesn't seem to change a whole lot, at least to the second decimal place, and neither does model year. Okay, the only variables that seem to change a little bit are factor origin. That's changed a little bit. Okay. But the biggest change we see in slopes is actually in acceleration. And we notice that acceleration, the relationship between acceleration and miles per gallon is 3 times, almost 4 times steeper for light cars than it is for heavy cars. All right. So the relationship between acceleration and miles per gallon is actually different for lighter cars and for heavier cars. Um, in the sense that um, for lighter cars, as the car gains more acceleration power, the log miles per gallon goes up, and for heavier cars, it hardly goes up. It's a much more flat slope. All right, it's only about 0.03. All right. Um, so this is again an example of a moderation. Now I'm using the word moderation and interaction a little bit interchangeably, but there is a difference between the two conceptually. All right. When we model this phenomenon of moderation, we often use an interaction term. So let's look at it on the next page. All right. So when we model a moderation, we usually create an interaction term. This term is called interaction, all right? When we say moderation, we're really talking about this phenomenon of certain things changing the relationship between two other things. And I haven't drawn the picture here, but I think maybe it was on the homework assignment. We saw it last time. So one of these, so in this, so conceptually, you may think of let me look at this total regression formula here. Depending on how you think about it, either weight is changing the relationship between acceleration or miles per gallon, or acceleration ability is changing the relationship between weight and miles per gallon, right? And the variable that you pick to be the variable that's changing the relationship, that's called the moderator, okay? When we write it as a regression, which one is the moderator, which one is the independent variable doesn't really matter, because in a regression, they both look exactly identical. Both variables are written as if they're independent variables with an interaction term capturing the moderation phenomenon. All right. Okay. So then for the homework assignment, we also asked, can we take a look at the interaction in three different ways? And the first way is just to do a raw interaction where I define my interaction term as just the multiplication of log weight and log acceleration, the two independent variables that are having this interaction effect. All right. And then all I do is I simply, and I'm going to just, I'm going to give it a name, weight times acceleration. This X here is weight times acceleration. It's just my naming system here. And I'm just going to add it to my regression formula along with everything else. All right. Now, before going to the mean centering and orthogonalization, are there any questions just about interactions and moderations? Let me just take a really quick break to ask, are there any questions about interaction or moderation? You can either raise your hand or you can just type a question. I prefer that you raise your hand if you are typing a question so that I know you're typing. All right. Okay, so then let's move on. Um, when we add this interaction term, we notice that it has an effect minus 0.28, minus 0.29, something like this, okay? And it's minorly significant, at least to alpha of 5%, okay? But what's more troubling is that once I introduce this interaction term, my slope estimates for weight and acceleration suddenly got thrown off. For example, you'll notice that weight has gone from minus 0.87. It had one of the strongest effects on log miles per gallon, and it's at 0.09 now. And in fact, it's insignificant now. And earlier, weight was extremely significant. All right, it had a very tiny p-value. It was very significant, and now it's completely lost significance. And I should have shown you the standard error here, perhaps instead of the p-value. But essentially, what's happened is that the standard error has gotten inflated tremendously because of multicollinearity. All right. I haven't shown the actual correlations here, but let's see if I have them down here. So here's my interaction term, and I can see here that oops, I'm looking at the two of the same thing. This should be, I need to fix this really quickly. Wait. Okay, so I can see here that weight has a small correlation and acceleration has a very large correlation with this interaction term, okay? But regardless of whether it's even the small correlation itself has produced a huge effect here in terms a huge difference here in terms of how what has happened to weight. In fact, it's had a really big effect, even with a really big change, even with a very small correlation with the interaction term. All right. And acceleration has also changed as we've gone from 0.05 and not being significant. And now the acceleration is like 2.35 and its p-value has dropped quite a lot to the point that it could be, if you care about 5% significance, it's actually significant now, right? So these changes in estimates, changes in standard error are all because of the of variance inflation that is caused by the multicollinearity with the interaction term. All right. And last time we discussed this is a huge problem with interaction terms. Interaction terms do actually help us model things more accurately, but they're often very hard to represent in a regression formula because they're so highly related to the terms that were used to be multiplied together to produce that interaction term. Right? All right. And I just want to reiterate again, just as we saw with multicollinearity before, we looked at multicollinearity before we looked at interactions. We saw multicollinearity just between multiple variables in a regression, with between what was it, between weight, acceleration, horsepower, cylinders, right? Like, and was there one more? Displacement, not acceleration, excuse me. Between weight, displacement, cylinders, and horsepower. Between these four variables, we'd seen a multicollinearity before. And at that time, our solution was pretty simple. We just dropped all the variables except for weight. We did that stepwise VIF thing, and we just dropped all the variables apart from weight, and we were pretty happy with that. We knew, though, that we're losing some meaning, right? Like, because displacement is more than just weight, it has another meaning to it, and we just lost that meaning. We lost the meaning of horsepowers, we lost the meaning of cylinders. And why were we okay to lose these things? Well, we said it's okay to lose these things because they're so heavily correlated with weight that weight can kind of capture a lot of their meaning. Not all of their meaning, but it can capture a lot of their meaning. However, that can be a little unsatisfying because, as many of you pointed out, weight is not the ultimate reason why maybe the miles per gallon has changed. Weight might be also the result of changing the number of cylinders or the displacement of the engine. So that's why weight has changed. So we weren't happy at that time that we had to drop all those variables. We lost some meaning. The story was kind of different. But we said it was a good first start at trying to handle multicollinearity. All right. Now with the interactions, we don't have that luxury of just dropping things. All right. If we dropped weight or we dropped acceleration, it would be a little inaccurate then to look at the interaction because these three things are correlated. So if you drop one of them, then the other two, let's say we dropped weight, then the other two would just pick up the effect of the variable that you dropped, and it would kind of take its meaning. So it would, in that sense, give us a false sense of what acceleration or this interaction term was. When you have an interaction, you must control for the two terms that were used to produce that interaction. All right. Without one of those terms, the interaction would just kind of, in another way, inflate to take on more meaning of the term that you dropped. So in the case of having interactions, we don't have this luxury of just dropping a variable. We have to have all three variables. So we cannot use that earlier trick of just dropping some variables and saying, oh, that's fine. All right. It would not only change the meaning, it would completely change the coefficient, and give us a mistaken sense of what this means. All right. And this is a known problem with interactions. So last week we looked at a couple of possible, I'm going to call them solutions, but before we go on, I have to clarify that there is really no statistical solution to multicollinearity. Multicollinearity is simply two things behaving so similarly that you can't distinguish the two. All right. Um, and that is not a statistical problem. That's just a problem we have with human perception of reality. So there's no statistical solution to that. The only thing we can do about multicollinearity with statistics is just to say, well, what information we have, let's try to interpret it a little bit more easily. So the two tricks we kind of looked at, one was mean centering and the other was partial orthogonalization, are essentially two tricks to help us interpret the results a little bit better. And let me show you let me just kind of see what happens when we do this. So mean centering, we just take log weight and we subtract from it the mean of log weight. Another way of doing that, I don't know if it's an more readable way or not, is to use a scale function and tell it don't actually divide by the standard deviation, just do the mean centering. All right, so the scale function will do just mean centering for you if you say scale equals false. If you don't say scale equals false, it will mean center it and divide by the standard deviation and give you standardized values. All right. But if scale equals false, we get mean centered values. So log weight, the MC in my code just means mean centered. All right. And then we have, and then I did the same thing for acceleration. So we just mean centered the acceleration. All right. And then we produce an interaction term, which is really just the product of the mean-centered variables, right? And we run the regression using the mean-centered products, or the product of the mean-centered terms, all right? And when we do that, let's take a look at what we have here. What we have here is that the interaction terms effect actually hasn't changed at all. It's minus 0.287. That's exactly what we had before with a raw interaction. All right. What has changed is that log weight's slope is back to being quite similar to what it was before we threw in an interaction term of about minus 0.87. All right. And it's off by a little bit, 0.88, but okay, fine. It's quite similar. And log acceleration is again back to being much closer to what it was originally, about 0.05. All right. Um, so we've kind of improved things a little bit, maybe not tremendously, but and the p-values are a little bit more reasonable to what they were before. But mean centering does a good job, but doesn't take us quite all the way there. All right. But it is probably the most common trick that you will see in regressions when people are using interactions. So one of the most common things is do the mean centering. And the other trick that I showed you was to do this orthogonalization, which is this, at first, strange operation where we simply regress the raw interaction term over the two terms that were used to be multiplied together to produce that interaction term. All right. And what we do is we just store the residuals of that regression. And what are the residuals? Is basically the portion of the interaction term that is not correlated with weight and not correlated with acceleration. Because remember, one thing that regression does is it produces residuals that are orthogonal or completely independent of the independent variables themselves. All right, so the residuals are they are a vector that's at 90 degrees to both weight and also 90 degrees to acceleration. It's unrelated to either one. As weight goes up or acceleration goes up or goes down, the value of the residuals doesn't change according to that. So the residuals are independent of these things, yet they are a part of acceleration. All right. If we wrote this out as a regression model, and statistically, it would be this interaction term is regressed over log weight plus log acceleration plus an error. So those three things together build this interaction term. We're simply taking out the part that is not related to weight and not related to acceleration, right? So that is our residuals. And it's an interesting view of residuals. The residuals is often treated as an error. We just throw it away. But in this case, it's the most meaningful part of this small regression that we have here. So that's kind of interesting. So we save those residuals, and we actually never examine the coefficients of log weight and log acceleration in this interaction, in this regression, because we're just not interested in them. We're only interested in the residuals. All right. So we hold on to those residuals, and those residuals actually become the components of the interaction that is most meaningful to us because it's unrelated to weight and acceleration. So when I throw that into my original regression with weight, acceleration, and year and origin and everything, then we find that this, oh, excuse me, this is written wrong. It should be weight times acceleration orthogonalized. Now once again, my interaction term is what it's been the whole time. It's not changed, but my weight and acceleration are almost back to identically where they were. Like it's much, much more similar now to my original regression without the interaction term. All right. So the advantage here of doing orthogonalization or mean centering is that within one regression results, I can interpret correctly the influence of weight, the influence of acceleration, and the influence of the interaction. All right. If I didn't do mean centering or orthogonalization, could I do the same thing? Actually, I could, but I would have to look at two regression results. I would have to look at the results of the regression with the main terms only, and this is where I would have to interpret the effect of weight and the effect of acceleration. And for the effect of the interaction, I would have to look at this second regression where I have this interaction term introduced. And here I would have to ignore log weight and log acceleration because I know that due to multicollinearity, they would have changed. All right. But if I wanted to look at all three, the weight and the acceleration and the interaction in one regression, then perhaps the mean centering, or even better, the orthogonalized technique gives me all the results I want interpretable in a single set of regression results. Okay. Okay. Um, all right. So we have a question here. So Yenu asks a really nice question. In what circumstances should we use mean-centered or orthogonalized interactions? Should we not use raw interactions? If we use both, how to choose between the results of the two? All right. So let me try to answer the question as directly as possible. I would say that you should just prefer the orthogonalized interaction at all times, simply because it gives you all the terms interpretable right away, and it gives you results and for the main terms, it gives you results in terms of the estimates, the standard errors, and the p-values that are closest to the regression that didn't have the interaction term to begin with, okay? So it gives us the most interpretable results. So I would just go with the orthogonalized term every time when we're doing an interaction. The only reason I showed you the mean centering is because it's just so commonly used by people, and I think it's commonly used for two reasons. It's commonly used because there are a whole lot of people out there who think, and they're obviously not statisticians, they're applied statisticians like me perhaps, who think that it's curing the multicollinearity problem. It's not curing it, it's simply giving you more interpretable results. And if that's what you're interested in, orthogonalization will give you even more interpretable results. So I would always go with orthogonalization if you are going to throw an interaction term into your regression formula. All right. And I think that question just answers all of them. Would you use the raw interaction ever? I suppose you could. Um, and one good use of it would be to maybe to demonstrate for people that there is a multicollinearity problem. All right. So that might be a good use of it, is to just demonstrate that there's a multicollinearity problem. All right. But if you want to just get over that and jump straight into interpreting your coefficients, just go with orthogonalization. But keep in the back of your head that you have not solved the multicollinearity problem, because multicollinearity is simply two or more things moving at the same time. You cannot solve that statistically. So these coefficients have to still be treated with some suspicion. When we took the orthogonalized interaction term, realized that we have chopped away from it two of its components and kept its third component. Kept only one of its components, which is the residuals. Okay, and and that's a sacrifice that we made. So we lost some of the variance and some of the meaning of the interaction, but we had to because there's no other way to bring it into our regression. So that's an unfortunate result of multicollinearity, and we just cannot really solve that statistically in any way that I know of. All right, so just keep that in the back of your mind and don't think that you have solved the multicollinearity problem. All you've really done is ensure that the coefficients are correctly interpreted, knowing that some of the interaction we've just had to throw away because it's heavily collinear with weight and acceleration. All right? Okay. So Guild asks, if there is no multicollinearity problem, should we still use orthogonalized interaction? Fantastic question. Um, I think you should, and I'll tell you why. Because we sometimes think that we need a very strong multicollinearity to kind of screw up our results, but it often doesn't take a very strong correlation. So for example, we saw that log weight was actually only very minorly correlated with the interaction. It might be tempting to say here, oh, the log weight is not going to have a problem, acceleration is going to have a problem. Whereas in reality, they both had a big problem. Okay, so multicollinearity affects your regression in sometimes, for humans, unpredictable ways. So I think it's best to perhaps do the raw to do the to do the regression without the interaction and do the orthogonalization at least as well, maybe even with the raw interaction. So at most, you will want to do this regression, and then this orthogonalized regression if you really want to show everything about this story. But if you don't have space to do all that and you want to just jump into the interpretable results right away, then at least do this regression, well, at least do this regression, the orthogonalized one, all right? And that will kind of give you the most interpretable results. And I wouldn't assume that there's a multicollinearity problem by just looking at um, the correlations, because as you just saw, even small correlations can produce some interesting results. Okay. And one more thing to remember, correlations don't capture all the overlapping relationship between the interaction terms and the main effects. Because remember, correlations really show you a linear relationship, right? There can be a nonlinear relationship between them as well that is not captured by these things. So don't just look at the correlation and assume that's telling you how much they are related. That's just telling you how much they're related linearly. All right. So I would suggest still go through this whole exercise if possible. All right. So Gil's question is, can we say that using orthogonalized interactions is a good way to inspect the multicollinearity? No, because once you've done the orthogonalization, and if you just look at these results, you don't really know how much multicollinearity there was or there wasn't. If you really want to dig into and observe the problems of multicollinearity, then you want to do the raw interaction term regression, and compare that to doing the main terms only. That's where you'll notice the coefficients have changed and the standard errors have changed. And that's what you can use to diagnose and say, yep, there was a multicollinearity problem here. All right. So fantastic. So let me kind of summarize all the questions by saying there's two things. One is diagnosing that there's multicollinearity. If you want to diagnose it, you will want to do the main terms regression and the raw interaction regression. You can diagnose it with that. Right? And if you want to move on and say, okay, finally, let's look at all the interpretable results and use what we can, then use the orthogonalized results. All right. So that's my suggestion of how to do them. All right. Great. Okay, so that's our discussion then about uh, interactions and multicollinearity. We may come back and see interactions later this semester. There's not too much later in the next two lectures or so. But just to give you a first glimpse of it and also a first glimpse of how to kind of solve it. And I thought that this exercise of showing you how to deal with multicollinearity in this way is also really interesting because it's gives us a lot more insight into what regression is doing, what these residuals are, and other things. So I think this is a really interesting exercise altogether. Okay. All right. Let's just clear up our heads and we're going to go into something different in a second. So let's just clear up our heads and take a little stretch break in your seats wherever you are. Yeah, and just kind of refresh ourselves a little bit. Um, and and then I'll kind of move on to something else. And after that, something else, we'll take a solid break. Okay. Um, So I hope you all have some water or some tea or something that you can by your side. And I hope that all of you are taking as many precautions as you can against COVID these days. Um, I don't want to turn this into a gossip session, but we can all see the numbers are somewhat stable. We're still getting hundreds of cases every day, all right? But it's really important that um, you stay maximally safe. And one bit of advice that I can just give, just having kind of lived through the onset of COVID in the US, is really learn to isolate yourself and don't apologize for it. um, uh, there will be people who will say, "Oh, it doesn't matter. I'm safe. I haven't really been going out, so we can hang out." And it's very tempting to say, "Oh, okay, okay. If you're isolating and I'm isolating, we're both safe." And that's actually not true because you really don't know what other people are doing, and people can tell you that they're isolating, but they may have gone to kind of meet with their close, like with their brother or their sister. And we often have this kind of conception that, well, our family is safe, their family. Well, COVID doesn't know whether you're related to somebody else or not. It doesn't really care. So it's really easy to kind of for it to kind of creep into our social network. And when I was in the US, I found that was or when I'm looking at stories coming out of India right now, which is having huge problems with COVID, that's kind of what we see is people are getting infected because they assume that their relatives or their best friends are safe. And you don't know who other people are hanging out with, and they're not telling you the full story. So the best thing to do is um, just unapologetically tell people that, hey, I'm going to be really rude and I'm not going to spend time with you physically. But actually, you can what you could do if you really feel very isolated is, of course, you can go online. That's one thing. Um, Another thing you could potentially do, but you have to be very careful, is you could go out to a public place and just stay very far away from each other. Keep a 10-foot distance from each other. Keep your masks on, and you can kind of walk around, make sure it's an outdoor area. There's a lot of breeze, and you're probably likely safe doing that. Okay. But yeah, huddling together as a group is really unadvisable right now. So and it feels very unnatural for us to have to behave like this with each other. So it's very tempting to say, okay, fine, let's just get together. But that's exactly how mistakes happen. All right. Those of you living in Shinju, you've probably seen that the numbers for Shinju are very low, like 0 or 1 every day. It means nothing because there's literally a bus stopping every 10 minutes from Taipei to Shinju and people getting off of it from Taipei. So there's no difference between Taipei and Shinju. We just haven't detected all the cases in Shinju yet. Okay. So just take extra precautions. Don't bother apologizing to people. Just be as rude as possible and say, I'm not hanging out. I just can't hang out. Okay. And it's the pressure of having to spend time physically with people is unfortunate. Okay. The last thing I'll mention about that is I really hate the term, what is it called? Social distancing. I think the better term is just physical distancing. like be social, but just be social online or at a great physical distance, okay? But just don't be physically close to each other. And keep your masks on all the time, all right? Okay, great. So that's enough of that. Let's move on to other things, all right? Yeah, I see what you're saying, Edgar. It is unfortunate. A lot of people are going out. They're doing outdoor activities because people feel outdoor activities are safe. However, if you're getting close to people, it's not that safe either. So you want to really keep a distance from one another. Okay. All right. Okay. Let's move on then. Okay. I had a topic at the end of last week which I didn't cover, and I'm going to try to cover it today. And let me just tell you a story, and let's try to use a story to motivate kind of what's happening here. All right. So the story, and this, I'm sorry, the slide is a little confusing. So let me kind of break this down and look at it in a few parts. Okay. So let's start with the story. So let's imagine that there's a shop where that is doing inspections of cars. So every year they inspect your car, and if there's any problems with it, they'll fix it for you. So this story is not about going to a car mechanic when something bad happens. It's about going to a car mechanic once a year to do your regular inspection, at which point they may find some problems with the car, or they may not. Okay, and there's a car company, and the story goes that there's an analyst at a car company, at a car repair shop, which is doing these annual, but it doesn't have to be annual. A lot of us don't go in every year. Some people may go in every 2 years, every 3 years, because nothing went wrong in those past years. And they're doing inspections, and they're repairing anything on those regular inspections, okay? And an analyst at this car repair shop wishes to explain how to customers, wishes to, because let's imagine customers are complaining that, hey, I came in to do some repairs and to do this inspection that you're offering, and I noticed that you're charging me more money than my friend who came in yesterday to do an inspection. How come you're charging me more? That's not fair. And what this car repair company would like to try to explain to customers is that, look, it's been many months since you last came in to do an inspection, and that's part of the reason why the cost is more, right? You've been gone for many months. We haven't seen the car in a long time, so many more things could have gone wrong. So we had to like be more careful. We had to find a lot of weird things. We had to like, it just took us more effort because you waited so long to do this inspection. And so that's the reason that the repair cost, the inspection and repair cost, is higher for you. So basically, there's a relationship between the number of months that have passed since the last time you did this inspection and repair and the cost of today's inspection and repair. So they'd like to kind of explain this statistically, and just to make sure they're not telling the customer a complete lie, they want to also kind of run some analysis to make sure that's actually true. All right, because that's the story their mechanics are telling them. So the analyst wants to make sure, yeah, is this statistically true or not? So let me kind of go to my data set here. So I'm going to just read this repairs data set. There's a whole bunch of things in the repairs data set, but there's only a few things that I'm interested in. All right. So when I look at this, the repairs data set is a very small data set. Okay. It's a toy data set. And in it, we have variables called repair time, which is months past, repair time, type, person, and cost. For this first regression, I'm only going to look at months past and cost. And months past is how many months have gone by since the last time you came into our shop. And the cost is how much are we charging you? And I take it this is in US dollars, not in Taiwan dollars, okay? And how much are we kind of charging you for the repairs, all right? And what we're going to do is we're going to run a very simple regression. It is literally a simple regression of and in this simple, actually, I've got a mistake here. Excuse me. Um, actually, let me run a slightly different regression here first. Okay. Um, Let me just run it in code here. Let me just run it here live for you, where I'm going to actually look at the cost as it's regressed over months past. Okay. And what we find here is that, I should look at the summary of this if I want the full story here. And what I find is that the number of months that have passed does affect the cost. And there is a somewhat significant relationship between the number of months that have passed and the cost. Okay, so for each month that has passed, the cost kind of goes up a little bit. All right, and that's the story here. I apologize here that I've kind of shown a different regression here. The regression that I've shown on this on the handout is still a useful one, and it's an important one, and let's take a look at that. Um, Here, the story is that the months that have gone by have basically affected how much time it takes me to do the repair. So, oops, excuse me, months. I've got to change my code a little bit. So this is telling me that the months that have passed since the last time we did the repair is increasing the amount of time it takes me to do the repair, which may be one explanation of why the cost has gone up as well. All right. So there's two ways to kind of so there's two stories here. One is that it's been a lot of months that you've gone by, so the cost has gone up. But why has the cost gone up? Well, maybe the more direct reason, and a mechanic points out that the direct reason for the cost to go up is that it takes more time to inspect and repair the car if you've been gone for a long time. So another way of explaining why the cost has gone up is because the repair time has gone. It takes more time to inspect and repair the car if you haven't had it looked at in a long time. So that's this regression right here, where I'm regressing cost over repair time. And when I look at this, I also find here a very strong relationship between the repair time and the cost. All right. So there's a few stories going on in here. One is that customers are saying, why is it costing so much for me to do this inspection and repair? And one thing we could tell people is that, well, it's been many months since you last came, and there's a lot more work to do, and therefore the cost has gone up. But maybe a more direct explanation is it's just taking us more time to inspect and repair your car. That's why it's costing you more. All right. And if you put these two stories together, well, what it's basically saying is that the number of months that it's taken, the number of months that have passed since we last inspected your car, is indirectly affecting your cost. Indirectly, because the number of months that have passed is really increasing the repair time. All right. And repair time is the more direct explanation. It's taking us more time to repair your car. We have to pay the mechanics. It takes, and there's maybe a little bit more in terms of parts and oils and things that we have to use. So that repair time is also is the more direct explanation of why your cost is going up. All right. Now, the analyst is having a little bit of a problem. Well, there's a couple of things here. There's months that have passed. There's the repair time that's also affecting costs. Which variable should I use to kind of explain what's happening here? A tempting way at solving this problem is to have both variables in the picture and to say that, well, the number of months that have passed and the repair time are both important. Yes, the number of months that have passed is an indirect explanation and the repair time is a direct explanation, but they're both explanations of cost, okay? So this might be a tempting way to model the problem, is just to kind of regress both months passed and repair, to regress cost over months passed and repair time together, all right? And if we do that, here's the results. And we notice something problematic right away. We notice that the coefficient for months passed has changed a lot. Oh, well, excuse me, that's not the right regression. When we looked at cost and months passed and cost, the relationship was like 2.9 something. These are unstandardized values. Okay, it was 2.9 something. And now it's like minus 0.05 something. That's weird. It's not only changed, it's become negative now. All right. And repair time is, okay, it's kind of similar to what we had before when we had a simple regression, all right? So what's going on? Obviously, what's going on is multicollinearity, all right? So once again, we're kind of seeing this multicollinearity problem, which we've seen twice before already. The first time we saw it, we just dropped some variables and we were happy and we moved on. The second time we saw it with interactions, we did this orthogonalization trick. This is the third time we're seeing it, and we can't really do an orthogonalization trick. This is not suitable to do an orthogonalization trick here. We don't also want to drop a variable because now the analyst is a little confused because these are both important variables. One is just an indirect explanation and one is a direct explanation. So how can we model this? All right. So let's take a look at this problem. Excuse me. And by the way, down here, I'm kind of showing you the correlation between the two independent variables, months passed and repair time. There is a fairly high correlation, about 0.73. All right, so putting them together in the same regression is probably not tenable. We cannot really do that, okay? And we don't want to drop it because we did hear that months passed. Remember the analyst, the story the analyst wants to tell is that the number of months that have passed is what's increasing your cost. So we don't want to drop that variable because that is the variable we really want to explain to customers. However, if we model it by itself, we're ignoring the direct explanation of costs, like the most obvious explanation, which is the repair time. So what can we do here? So I'm going to show you here a slightly different strategy of modeling this problem. And it's going to be different in this sense. It's going to be different in that we're going to model two regressions rather than one regression. All right. So one regression we're going to model is going to be the regression of how the repair time is affected by the number of months that has passed. All right. That's going to be one of our regression variables or regression models right here. It's how repair time has changed. Okay. Oh, I've got my little handy dandy thing. How repair time has changed, and repair time is down here, based on the months that have passed. All right. So this is one regression that I'm going to look at. The second regression I'm going to look at is how the cost has changed based on the repair time. All right. These are two separate regressions, unfortunately, but this is the most accurate way of explaining what the mechanics are telling the analyst. The mechanics are telling the analyst, yes, the months passed is affecting the cost, but only indirectly, because what's really happening is that the number of months that have passed since we last inspected the car is increasing the inspection and repair time of this car. And that's what's changing. That's what's directly responsible for changing the cost of these repairs, right? And but the analyst is at a little bit of a problem because what they really want to explain is months passed and how it's affecting cost. All right. And as we saw in the previous slide, we can't put both these variables into the same regression because, well, they are highly correlated is one problem. But the other problem is it's inaccurate to perhaps show them as a single regression because really months pass is affecting repair time and repair time is affecting cost. So this is an inappropriate, so what I've drawn here is potentially an inappropriate way of, can I do this? Yes. This is an inappropriate way potentially of modeling this problem because it's not showing the direct and indirect relationships that are present in our problem. All right. So the more accurate way of showing it is as two regressions. And here is where path modeling, this kind of visual representation technique that I showed you earlier, really comes in helpful because the path model shows us in one picture the whole problem. The path model tells us that really what's happening is that months pass is affecting repair time and repair time is affecting cost. So months pass is really indirectly affecting the cost. All right. Is there any question about this conceptual model that I've drawn here with a path model? There's an indirect relationship between months passed and cost. And it's indirect because what's really happening is months passed is directly affecting repair time, and repair time is directly affecting cost, okay? All right. So we have two regressions here, and we can run them separately, months repair and time cost. Months repair is the repair time regressed over months past. That's this relationship here, okay? And this regression here is the cost regressed over repair time. That's this relationship right here, all right? And so what we are getting here is a coefficient 0.30 between months past and repair time, and we're getting a coefficient here between repair time and cost. Notice also that they have different units. This coefficient, its units are time over months, right? That's the slope, is how much time takes depending on how much for every additional month. And the coefficient here, its units are in dollars over time. It's how much is the cost affected for every unit of time. All right. So these are two separate regressions. But how do we now tell a story about how months past affects cost? Well, there's an interesting thing we can do. We can find the indirect relationship of how months affects cost through the repair time, because of the repair time, by actually multiplying these two paths together. When I multiply this coefficient by this coefficient, it actually tells me the indirect effect of months past to cost. All right? And let me say this in two different ways. The simple statistical explanation of this is cost is affected by repair time, cost is affected by repair time by this amount. That's the coefficient that explains it, okay? But repair time is explained by months past by this coefficient. So it makes quite a bit of sense that to translate months past to repair time, I have to multiply months past by this coefficient, and that'll give me an estimate of my repair time due to months cost, and then I have to multiply it by this coefficient to translate it into how much that translates into dollars. All right. And that's exactly what we're representing here. The cost is affected by months past indirectly by multiplying these two coefficients together. Okay. We have a question here, and I'll address this in just 1 second. All right. So if I kind of do this statistically here, so let me I did my months time regression here, I did my time cost regression here, and now what I can do is from each of these, I can extract the coefficient, so I can take the months repair regression, and I can inspect its coefficients. Oh, excuse me, I've misnamed this variable here. Is it months time? Okay. Okay, excuse me. So, hold on. Dollar coefficients. Okay, so I've got intercept and I've got months passed. All right. And if I want this, I get two coefficients, one for the intercept, one for the actual variable. If I look at the second coefficient, then it gives me just the months passed. Similarly, for the time cost regression, I can get the second coefficient, and that's with repair time. Okay. And then I can multiply the two together. An unfortunate thing in R is that when I multiply the two together, it picks one of the labels and attaches it to it. And I don't want this label, months past. It's not months past, actually. So what I'm going to do is I'm going to run this multiplication, and then I'm going to unname it. I'm going to take away any labels from it. So it just gives me the raw number, 2.95. All right. So 2.95 is actually the coefficient that explains indirectly how months past affects cost. Now, Hannah has a really good question, and I'm just going to show it on screen here. So Hannah has a really good question about how do we define which one is direct and which one is indirect. All right. And Hannah, the explanation and the which one is direct and which one is indirect would require some knowledge about how cars are repaired and how that affects costs. As somebody who's just doing applied statistics, I wouldn't be able to answer that question. However, in my story, I have said that mechanics are telling me that they understand the situation well, and they're the ones telling me that actually the cost is due to the repair time. Like that's literally how we compute the cost. It's going to be the repair time and some other things. It's going to be repair time and parts and maybe some other things that are also involved. Maybe some tax and maybe some insurance details. We don't know all the things, but repair time is really what's directly affecting the cost. And they'll tell you that, yeah, when we're doing the invoicing, we're not really using the months past. Now, the analyst is the one who wants to tell the story about how months past affects cost. So the mechanics are telling the analyst that no, no, months past is really the indirect explanation. What's directly affecting the cost when we're doing the invoicing and all the complications that go around it is actually the repair time. All right. So Hannah, the explanation for this is not a statistician cannot answer this question. A domain expert, in this case, the mechanics working in the car company, can tell us which is direct and which is indirect. Okay, that's a really, really good question, though. All right. So here, the indirect effect of costs of months passed on cost is 2.95. Right. So this is another way of, this is a unique place where we can handle this multicollinearity issue by actually splitting it into two regressions, because we have a strong domain understanding, and by domain I mean the field of car repair, I guess, which tells us that actually these are two separate effects. One affects A affects B, and then B affects C, and that's how we can model it in this case. When we have this very strong understanding that there is a causal chain and one thing is affecting another thing, and that second thing is affecting the outcome. All right. So this is a place where we can use this, use these kind of indirect effects. All right. Any other questions on indirect effects? Now, to be clear, we could just regress cost over months past directly, right? We could do that regression, and I think I did that sometime before, where we just looked at months past and how does it affect cost. We can look at it directly, and we get like 2.93 something. It's, oh, excuse me, it's not entirely different. Oh, it's not entirely different from what I'm getting here, right? However, that direct relationship may be inaccurate because maybe months past is correlated with cost for some other reasons apart from repair time, and it's not, maybe it's not appropriate to look at it directly. All right, so that's entirely why we're looking at it indirectly. All right, excuse me, I keep jumping to the wrong slide here. I apologize. All right, so that's why we're looking at it indirectly. All right. So we're not interested in the total effect of months passed on cost. We're only interested in the indirect effect through repair time. In this relationship, repair time, which has a direct effect, is often called a mediator. A mediator, MED, med, is a word that we often use for something in the middle. All right, like in Chinese, zhong would be like something in the middle. So in a lot of European languages, med is something in the middle. All right, and to mediate is to like in if there's three people and two of them cannot talk to each other, they just hate each other, and they both talk to the third person, then that third person is often called a mediator because they have to listen to one person and then tell the other person, listen to the other person, go back to the first person. Okay, so that's a mediator. So this is often called a mediating relationship. So this is a nice way to have it, this kind of indirect relationship. Is there any questions? What is the difference between multiplication in moderation and multiplication of coefficients in mediation? Nice question. So in moderation, remember, we're not multiplying, so Meta, we're not multiplying coefficients. In moderation, we're multiplying the raw data with the raw data of another variable. So that's the multiplication of moderation. We're multiplying data with data to create a new data term we call the interaction term. All right. We're seeing multiplication here again, which is awesome. But this time we're not multiplying data with data. We're multiplying a coefficient with another coefficient. All right. So we're multiplying two relationships together here, not two sets of variables. All right. So that's the difference here. Metab, does that help? Okay. And you're welcome to ask a more specific question if you wish. All right. Okay. Great. So this is just one more thing I wanted to show you about relationships, and that they can be a little bit more complicated than what a single regression can hold. In this case, we had to do two regressions to represent that there is a chain of effects, one thing causing another thing causing another thing. Okay, and the last thing I'll mention here is that one problem with mediation and doing this kind of like multiplication is this coefficient that we get. It can be very hard to define what its standard error is, right? So we got this coefficient now, 2.95, okay? But the problem with this coefficient is that we cannot easily tell if 2.95 is just unique to our data set and our sample. What if somebody else collected, what if in another car repair shop they collected another sample? They would get a slightly different coefficient from us. Hopefully it's similar, but it could be slightly different. So what should we do? All right. And um, we could, on the one hand, maybe take the standard errors and somehow compute the resulting standard error of this. But what if there was many more regression terms? What if the models were not so simple, not just two simple regressions? What if there was more terms in the regression? Then what would we do? The calculation could get quite complicated. All right. So if we want to find out 2.95, how does this vary? Like 2.95 is for my sample. How would it be different for other samples? Well, we can go back to our good old-fashioned trick, the bootstrap. All right. And let me show you what the bootstrap would do for us. So here's a bootstrap function. And what it takes is two regression models. It takes the model between the indirect and the mediator, and the model between the mediator and the outcome. All right. It takes the two models, and you provided the data sets, and it randomly picks with replacement some of the data, and then it runs the two regressions. All right, with the bootstrapped data. Then it multiplies the two coefficients together and returns to you those two coefficients. All right. So let me see if I've done this correctly. I think I've got to rename one of my variables here. I think it's mistakenly named. All right, so here's my bootstrap mediation. I'm going to set the seed. All right. And now I'm going to call my bootstrap function, and I'm going to give it the two regressions. One from months past to repair time, one from repair time to cost. All right. And I'm going to, if I ran this once, it would give me a coefficient, twice, three times. So it gives me a different coefficient each time. And hopefully somewhere in the middle is 2.95, my original one. All right. So what I'm going to do here is I'm going to just run it this 2,000 times. And I'm going to get 2,000 estimates of this indirect relationship from months past to cost. All right. There it is. And here's the 95% interval of, this is where 95% of those values lie. They lie between 1.19 and 4.91. Hopefully 2.95 is somewhere in the middle. Okay. And I can plot that. All right. You will notice in my bootstrap, some values were actually there was maybe one or two values that were smaller than zero, all right? But for the most part, the most values are above zero. And if I look at the 95% confidence interval, then it's then we can say now that our estimate of 2.95 that we had before is probably significantly different from zero, at least at 95% confidence. Okay, and I could do this at I could do this at 99% confidence as well if I simply change this to 0.005 and 90.995, I think. All right, and let me use a dotted line here. All right, and that's like my 99% confidence interval. Okay, so I can say I'm fairly sure that there is an indirect effect and it's not zero. It's quite bigger than zero. All right. So last week we saw moderation. This is another thing called mediation. All right. Now, mediation is not a trick to use for multicollinearity unless you happen to know quite certainly that there is this indirect effects going on. In which case, it would not be appropriate to model everything in a single regression. We could model them as a sequence of regressions and then just multiply through the regressions. Okay. Any questions on any of this? Is everyone all right with what we have covered so far? Okay, fantastic. Um, you're welcome to write more questions. But what we're going to do now is we're going to take a little break. I'm going to take a 10-minute break. So it's now 10:28 on my clock. I'm going to get back online a little bit before 10:40 to start the next part of our lecture. All right. So uh, uh, please turn your video camera off during the break so we don't see where you're going. And more importantly, we don't see what you're wearing below your shirt because that's all we can see right now. And I'll see you back between 5 to 10 minutes. But please, after 8 minutes, get back online and start getting ready.